Hello and welcome. I'm Edmund from Square, and with me are Lak and Yufeng from Google. We're going to be talking to you today about useful patterns for developing, operationalizing, and maintaining machine learning models. Machine learning involves a few steps. From organizing your data, you gather it, engineer your features, create and train the model, and you finally deploy it. But it's actually iterative. You need to, there we go. I didn't know there was an animation there. It's actually quite iterative. You need to first organize your data, You're not done once you've trained and deployed your model. You need to continuously monitor its performance, add features, retrain periodically. It's a team effort involving data analysts, data engineers, and data scientists. Typically, your subject matter experts, your data engineers will gather all the data with inputs from data scientists. Your data scientists will join all the data, create the features, create and train the model, and data engineers will be responsible for maintaining the training and prediction infrastructure. And everyone will monitor model performance, although different aspects of it. Data analysts will be focused on the outputs of the model, their distributions, how actionable they are, whether they're enabling good decisions or not. Data scientists will be more focused on the distributions of the inputs themselves. Any shifts in those might represent a problem with your data ingestion pipeline, or maybe a shift in the population. And the data engineers will be focusing on uptime and resilience. And thus, because we have so many people working on so many moving parts simultaneously, operationalizing ML models is actually quite difficult. And now Lak is going to discuss some of those challenges.
Thanks, Edmund. Yep, so operationalizing an ML model, by which we mean after going from a trained model to a model that's deployed in production that you can use to make predictions with. That's hard, and that's like the chasm in our title, right? There's this big chasm between training the model and getting it into production, right? So let's talk about number one, or number zero. Why is it so hard to put a machine learning model into production? Okay. What makes it hard? I mean, this is software. We know how to deploy software. So what is so special about machine learning models that it's so hard to put them into production? So first thing is this whole concept of reproducibility. The thing is, when you train your model, what are you training on? You're essentially training on historical data, data that is in a data warehouse, right? You basically are taking that data, it's in a data warehouse, and then you're training your model on it. But when you come to predictions, what are you predicting on? You're not making your predictions on data in the data warehouse. That's historical data. What you care about is predictions in a real-time stream, right? You're making predictions on data that's coming in. So it may be software, but these two are different software systems. You have one software system that's about historical data and data preservation and so on, and you have another software system that's about real time, that's about getting things very quickly, that's about user interactivity, it's about speed, right? So they're very, very different kinds of systems. And everything that you do in the training step has to be repeated in the deployment step. And that reproducibility is very hard. So we look at patterns that help us get that reproducibility so that the steps that you did during training, you can basically repeat them or reproduce them in your deployment system. The second thing is that everything that you do needs to be portable between the training system and the deployment system. And unfortunately, these two things, the hardware and the software, are often very different, right? You might train on the cloud, but you might do an inference on a phone. Right? It may be the same software, but the software that runs on the cloud, obviously the system is very different than something that's going to run on a phone. right? And you need everything that you do, all your ML models, all your ML systems to be portable between the hardware and the software that's actually different between the training and inference systems. So we look at portability patterns, right? Ways to make sure that things remain portable. The third thing is that whatever platform that you use, it needs to be flexible. And the reason it needs to be flexible is that your skill sets on the training side and the priorities on the training side are very different from the skill sets and priorities on the inference side, right? On the training side, who's doing the training? It's going to be your data people. And what do they care about? Data, number one. But they also care about things like accuracy. Can I train on all the data? Right? They care about scale, but when they talk about scale, they're talking about scale in terms of, am I able to scale to all my data? They're talking about research. They're talking about being able to use better models, to be able to use the most advanced models that are available. And they're also talking about the models themselves, being able to basically accommodate them. So that's on the training side. So their priorities are in terms of accuracy, in terms of scale, in terms of being able to train on all their data. And their skill sets tend to be things like statistics and Python and so on. Now look on the other side. On the inference side, who's doing the inference? It's your engineering team. What do they care about? Resilience. They don't want the thing to crash. They don't want the pager to go off. Right? That's the number one priority. The priority is very different. They also care about scale, but the scale that an engineer cares about is different from the scale that your data scientist cares about. Your data scientist wants to train on all the data. The engineer wants to make sure that they can handle all million users that are going to hit your web page at lunchtime. Right? The scale that they're talking about is very different. They care about the engineering quality. They care about maintainability. They care about speed. They care about applications. Right? So the priorities and skill sets are different. And so if you pick a machine learning platform, any platform you pick has to be flexible to accommodate both of these types of users. Okay? And finally, you need to basically deal with agility. Right? And as this is kind of a joke, but you you train your model on historical data. You train your model on things that look like dinosaurs. And then you start running your model, and they basically are dealt with birds, right? Your data has drifted, has evolved over time, and you basically get something that is kind of the same thing, but not quite the same thing. And you need that agility to deal with this model drift, because guess what? The real world, things change over time. So the thing that you trained on and the thing that you're predicting on, there is going to be model drift. And the question is, how do you recognize it? How do you accommodate for it? How do you fix it? So we look at patterns that deal with agility. So first to talk about reproducibility patterns. Okay? So first one, so what are some of the ways that we basically get reproducibility? Okay? So first thing, is what we talked about. You train on historical data. You predict on real-time streaming data. So how do you deal with that? You want to basically reuse your pipeline, your data pipeline, your data preprocessing as much as possible between your batch historical system and your streaming real-time system. To date, there is still only one system, one API that allows you to do data processing with the same code on both batch and stream, right? And that's Beam, Apache Beam. In fact, the BE is, right? The B is for batch and the EAM is for stream, right? So it's about a single consistent thing that lets you deal with batch and stream so that you can basically have the same code. And in our case, we run Apache Beam on Google Cloud on Dataflow. That's why you see Dataflow in the diagram there. But the code that you write is open source. It's Apache Beam. So pattern number one, Apache Beam to reuse this pipeline code between training and inference. So the reason that we do this, right, is because all the data transformations that you need to do on the training data set, they have to get applied during inference too, right? So you take your raw data, you pre-process it, you clean it, you create features, and it is these features that you give to your training model. And now your training model needs to basically do predictions. And so you take that trained model and you deploy it, but to that deployed web application, what comes about is essentially the raw inputs that the clients need. It's exactly the same data that they need. The question now is, how are we going to do this pre-processing and feature creation? So that reproducibility is super important. How do we reproduce everything that we did in our training system on the inference side? So there are a couple of ways to do it. If, for example, you do pre-processing in TensorFlow, you can do this reproduction, right? So you have your pre-processing code, you have your feature creation code, and then you create your pre-processed features and you train your model on them. It is very efficient, and if you're using the estimator API, you basically have some things called feature columns, and everything that you do in a feature column will be remembered in the TensorFlow graph. So when you checkpoint a TensorFlow model, all of those pre-processing steps are saved in the graph, so that when you then go out to go predict it, it's automatic. All of those steps that you did get carried out because you used feature columns. So that is great, but there are a couple of caveats here. The first caveat is that it's only things that you do in a feature column. It's only things that you use TensorFlow methods with. What if you did pre-processing that doesn't happen in the feature column? Now you have to deal with it some other way. The second thing is, and this is a very general high-level restriction, your TensorFlow model, when you train it, what does it see? It essentially sees a batch of examples, but in essence, it only sees one example at a time. It doesn't actually see examples in order, right? So any of the pre-processing that you do on that one training example is fine. But if your pre-processing involves a moving average, will you ever have a moving average as an input? Sure, right? If you ever have a moving average, that moving average, the way you compute the moving average, there's nothing you can do inside the TensorFlow feature transform to do that. Right? It doesn't work because the TensorFlow model only sees that one example. It doesn't know how you computed that feature in the first place. Okay? So there is that second issue. So it's efficient, but it's restricted to TensorFlow methods in a feature column, and it's only that one input. The other approach that you can do is that you can do this thing in Apache Beam. So that's what I just showed you, right? You do it in that Beam pipeline. You do your actual pre-processing. You compute your moving average in Apache Beam. So that's great. It has state. You compute it in Python. You compute it in Java. And you compute that feature, and you train your model on the feature. Then when you're doing your predictions, you run the exact same pipeline to create the exact same moving average, and you give it to your model. So this way now, it sees a full data set, right? It scales really well because its Beam is distributed, but it cannot take advantage of accelerators. What do you mean by accelerators? GPUs, TPUs, etc. This is okay if it's a moving average. It's not okay if you're basically running the first half of the inception model, right, to basically create an embedding that you're basically using as an input to your model. Now that creating that feature is so expensive, you can't really do that in something like Beam. So how do we basically do reproducibility that kind of accommodates for both of these things? And that's what TF Transform does. So TensorFlow Transform is a library that is a hybrid of Apache Beam and TensorFlow. How is it a hybrid? You do your analysis during training in Apache Beam. So you can look at all your data set, You can compute your moving averages. You can find your mins and maxes. You can find your unique values. You can do all of those things in Beam. And then at prediction time, in TensorFlow, you can actually apply those transformations. So you get the scale of Beam, and you get the efficiency of TensorFlow. Right? And everything is remembered from what you did during training to what you need to do during prediction. Okay. So pattern number 1 for reproducibility, TensorFlow transform. Okay. So you basically get, as I said, the efficiency of TensorFlow during inference and the scalability of Beam during training. So it's not just Beam, it's not just TensorFlow, it's that right combination of the two. The second thing that you want to think about when it comes to reproducibility gets back into the development of the model itself. And this is where you want to make sure that you are never copying data. Because every time you make a copy of data, you run this risk that the thing that you train on and the thing that you're going to predict on, there have been other things that have happened in the middle. So one of the things that we always suggest is keep your data in BigQuery. You can share the data set. You can share your queries in BigQuery. You can actually save your data on cloud storage, and you can run a federated query. So you can run your SQL query on the data that exists already in cloud storage, or in Cloud Bigtable, or on Google Drive. But the point being, don't make copies of your data. Don't move your data around. Keep your data in place. Join it in place. Share the data sets. Share the queries so that different people can run different analytics on it. Okay? So join your data in place, don't move it around. So if you have structured data, if you have streaming data, use BigQuery. If you have archival data, unstructured data, use cloud storage. If you have transactional data, time series data, Internet of Things data, use Cloud Bigtable. If you have business types of data, spreadsheets, etc., use Google Drive. And the cool thing is that all of these things you can run a federated query on. Right? So you can keep your data in place and don't make copies of it. And by not making copies of it, you can limit your reproducibility problems. And then you can access that same data with different kinds of tools. So as we just talked about, you can do federated queries with BigQuery, but you can use Dataflow and Apache Beam so you can do your batch and stream processing. So you explore your data in BigQuery, and then you train and you predict with Dataflow. You haven't changed the data. You haven't moved the data. So you don't have to worry that this data that you explored and this data that you're training against are actually different. So you can do dataproc, Hadoop and Spark workloads, machine learning, etc. Okay? And this allows you to democratize your data insights across your org. You can save and share your queries. You can create good reports with BigQuery. You can share them as sheets. You can use partner tools like Tableau, Looker, etc. to share this data. But the key principle here is keep the data in place, do your analytics with multiple tools, but don't move your data around. Okay? And to talk about how Square does this, Edmund.
So the rules governing how much Square should pay its financial partners for processing any given payment are extremely Byzantine. They're scattered across multiple rule books, with each card network and currency having its own book. Some of these books are over 1,000 pages long, and they change twice a year, every April and October. So it's actually quite difficult for us to know how much we should be paying for any one payment. It's far too difficult to generate and maintain a rules engine. So what we've done is we've created a machine learning model to verify a cost for us, the transaction cost anomaly detector, or TCAD. Through TCAD, we've discovered over $2 million worth of transaction anomalies, much of which was recoverable because they were bona fide transaction cost errors. And a large part of achieving that result has been limiting training serving skew, which we've done by using the same queries, using the same BigQuery tables at training and inference. Therefore, at both times, we're using the same data. We've also performed all of our pre-processing within TensorFlow using the TF feature column module. And this ensures that at training and inference, we're using the same vocabularies for our categorical features, the same scaling for our numeric features. This has worked quite well for us, but it does require us to first define these vocabularies, define these numeric ranges, and encode them in our model. In future iterations, we're most likely going to be moving towards TensorFlow transform to further simplify this process. Now, another pattern that we've been using in TCAD is portability. And to see that, let's take a look at the TCAD architecture itself. Now, let's start at the top left with training. We have our historical cost data stored in BigQuery, and we're training with that data on ML Engine. And then when it comes time for inference, which is the lower half of this diagram, we have our trained model stored in cloud storage, and we have a data pipeline, a cloud data flow pipeline, which also takes our historical cost data from BigQuery, the same source as training, and computes or estimates what our true cost should be, compares that against our actual cost, computes aggregates, passes them all along to Stackdriver, where we have dashboards and alerts, and if necessary, additional human review and further action. This has all been working great for us, but we didn't start with that. We had to go from an on-premise solution to a complete cloud solution where we moved all our data to BigQuery, we moved our storage to Google Cloud Storage, and we moved our inference and data processing pipeline to Dataflow. But all along the way, we were able to retain the same TensorFlow model.
Cool. Thanks, Edmund. So as Edmund said, right, the key idea is this whole idea of portability, that they were able to make all these changes, but at the bottom of it, they were able to keep the exact same TensorFlow model. And that's one thing that I think you keep hearing over and over again, is this idea of being able to do porting from on-prem to cloud, from your cloud to your device, et cetera. And TensorFlow is a big part of providing that portability. So why do we need portability? Okay, when we designed TensorFlow, this whole idea was that we needed to support different training and inference environments. So when you talk about where do you train, you might train on the cloud, you might train on a Kubernetes system, right? You might train with programs written in Python. TensorFlow is all Python primarily. The training code might need accelerators like GPUs or your custom ASIC chips like tensor processing units. So you need that portability that happens. The fact that training happens on all these kinds of environments, then you go over to the inference side. Where do people do inference? Where do they run predictions? Well, they may run predictions in Kubernetes. They may run it on GKE with Kubernetes Engine. They may run it as part of a web application. They may run it in mobile devices. They might run it on JavaScript. How many of you heard of TensorFlow on JavaScript? TensorFlow.js, right? That's part of the portability idea. You train the model on the cloud, but you run it inside your web browser, right? You run it with Java. You run it. So the fact that you trained it, created a model with Python, doesn't mean that you have to run it in a Python system, right? That's a very key, important design goal behind TensorFlow, is to support all these different training and inference environments. So the pattern here is use TensorFlow. TensorFlow is what gives you that portability. And in terms of these environments, I like to think of it as 3 different types of environments. You have the environments that are all about simplicity, right? You have a fully managed Cloud ML engine. Everything is, you don't have to spin up a cluster. You just submit your TensorFlow code, and you have your model trained. Or if you want to do development of a model, and you just want a VM with TensorFlow and Jupyter and everything that you would typically need as in data science, you want all of that directly installed. There is a deep learning image. You can go to the Cloud Launcher page, launch a deep learning image, and it basically has different versions of TensorFlow, different GPUs that you can attach to it, and you can basically get going. So that's the simplicity end of it. On the fast side of things, you want to do things very, very, very fast. You want to train very fast. You have the cloud TPUs. You have GPUs on the cloud. But in between, you might need portability. You might need things. You may need to run inference not on the cloud, and that's where Kubeflow comes in. Kubeflow is TensorFlow in Kubernetes, an open source project led by Google. And then you have TensorFlow, which runs in Python and C++, in JavaScript, in Java, TensorFlow Lite, which runs on mobile devices. So you have all of these different choices. And third, to talk about flexibility, Yufeng.
Okay, so we've talked about our first 2 points. Flexibility comes in kind of almost when you reverse around, instead of saying, for the same model, if I switch the world around the model, what happens? There's also the consideration of when it comes time to change the model, how can we do that without then altering the world around that model significantly? So when it comes to model building, there's a very wide library of choices now, right? There's lots of different libraries you can use to build your model. You can use scikit-learn, you can use XGBoost, Keras, TensorFlow, and many others. There's also the TensorFlow Hub. If you haven't seen that, I would really encourage checking that out, TF Hub. It's a really neat place to kind of see the different models that folks are building. The hope is that you'll not only be able to get value out of the TF Hub to get models that are out in the community, research models, things like that, but also then be able to contribute back to the community things that you have found, the new models that you've developed. And so whether you're building just your standard fully connected networks or convolutional networks or more sophisticated things like recurrent nets and things like that, having flexibility in what model you use, because sometimes you might start with one, do your initial analysis, and then for the same type of data, change fundamentally the kind of model you're using. So that means you want to think about what kind of interface your model is providing to your downstream consumers, such that you're able to swap things out, right? Just general good software engineering practices when it comes to layers of abstraction and things like that. And the other thing I want to note is that Keras is now also part of TensorFlow. So you can call tf.keras, I think it was 1.8 and above, that supports that, and that there's interesting ways now you can combine model building using Keras. So Keras has a really great, simple model building API that is really easy to use, and you can combine that with TensorFlow's execution speed and estimator frameworks. You can stick a Keras model inside an estimator and then run that, which gives you access to distributed training, accelerators, all without having to rework the wiring of your model. And so that brings us to kind of the next point, right? Where do you hook up the model to? And the considerations around having flexibility in the consumption of your data. There's really highly structured data, right? It may come from a variety of different sources. And as you experiment with the type and amount of data you feed your model during this training process, this iterative process, you might find that you either need to add more data, change from one data set to another, or add something in, and that it may go from fitting into memory and being really easy to do on a laptop to being something significantly larger. Or maybe you go from having unstructured data that's in a data lake and you move to structured data, and then you have to think about how you're going to port that data over and connect that in. So having flexibility in how your model consumes the different types of data that it may encounter through its lifetime is an important design decision as you go about kind of this task, right? Swapping out models, swapping out data. And thirdly, the notion of being able to iterate quickly. So this is a kind of a specific note for more complex models. And when I say complex models, I don't just mean models that are in and of themselves sophisticated, quote unquote, but also situations where you have a requirement where you need to train a large amount of data and run that through the model during training before you can get a meaningful outcome, or to even know if your training is kind of going in the right direction. And so for that, you want to be able to train and iterate with a reasonable amount of speed. And there's a couple ways that you can achieve speed, right? If you say, well, training iterations are fast for me because each time I do a new training cycle, it only takes 30 seconds. Great, you're all set. And so you can just try something, try something, try something in series. But what if each time you do a training cycle, after you've already maxed out all your options when it comes to compute resources, it still takes 30 minutes? or 30 hours to do one training iteration. That's when it comes times to think about other ways. You have to think outside of just doing one attempt and then a different attempt and moving on. And so being able to kick off multiple training jobs in parallel that are isolated from each other such that you can experiment across a spectrum of different models, different parameters, and potentially even different features, right? Different input datas that go into your model. And so one kind of plug I'll make here is that Cloud ML Engine supports kind of these various facets of quick iteration when it comes to larger data sets and bigger training jobs. You can train multiple jobs. You kick off a job, you configure it with your model, you feed it your data, and it's off to the races, and then you can set up another one. Right, you kick off another job, and you can choose to use the same data set or maybe a different data set, same model, a different model, et cetera. And you can kick off multiple training tasks. But then with each training task itself, you can also configure different hyperparameters. So there's built into ML Engine a hyperparameter tuning service called HyperTune, fittingly, and it will basically try out different variants of the same model and try to help you, guide you in which set of hyperparameters would be most appropriate. And it'll basically do these in parallel. So you're kicking off parallel jobs. Each parallel job is kicking off parallel jobs in itself. Right? And so you're getting this incredible scaling effect and making yourself super, super productive, which means you can just go make a sandwich or something at that point. Okay, so the other piece of flexibility I want to point out when we talk about model building, now we flip over to deployment. When we're making predictions, making inference, there's a couple of different options and things you want to keep in mind. Right? One is model stacking. Once your model is deployed, it may be in a situation where you actually have the outputs of one model feeding in as inputs to a second model. And maybe that model's outputs feed into a third model. And at first, you might look at this and say, that's too sophisticated. I'm not going to have 3 models feeding each other. That's silly. But a lot of times, the things that we do in the pre-processing step can actually be thought of in this context. What is the first thing that happens to your data when you make some of these transformations? Depending on what they are, if they're not something super trivial like the time series averaging, right? If you're doing something a little more sophisticated, then you could think of it as you are kind of modeling your data in some way, right? And that might change. And you're going to need that to show up in deployment as well. And so when you have that situation, the interfaces between your different models, they need to not encounter bottlenecks. Because at deployment time, any bottleneck starts really accruing and your latency starts building up like crazy. And then the second point is swapping out models. Your data science team goes and they've developed a model. Here I'm calling it model 4 because it's the next number. And then they, a couple weeks later, they're like, hey, we found some new data. It looks kind of different, and we decided to try out a totally different model. The interface is kind of similar, but it's a different model. It's really different. And so we need to swap it out live. Can we do that? Right? So what happens when we want to swap in model 5 like that and still have everything keep working? And so if you're in a situation where you should be able to do that, that's something you have to engineer up front, because if you don't and you need to do that, you're going to be in a hole. And thirdly, scaling the inference, right, or predictions. When you have lots and lots of requests, standing up a production server is no easy feat, but standing up multiple really quickly, because lots of requests are coming in, is arguably even harder. And so the other side of ML Engine, aside from the training and the GPUs and the TPUs and all that awesome stuff, is that you can take an exported TensorFlow model and just give it a name and point to it and say, here, ML Engine, take that model and deploy it for me and auto-scale that for me. And yes, I would also like a REST API for that. And obviously it should be secured. And you can just take all those things for granted. You literally just give it a name, put down the path to the file, and click save. So with that, I'll pass it over to Edmund to talk a little bit about kind of how they implement kind of flexibility at Square.
So 2.75%, it's what Square's famous for. It's what we charge for processing in-person card payments. But as you can see from the smaller text below that, we actually offer custom rate packages as well. And generating those custom rate packages relies on model stacking and model choice. Let's start and walk through this diagram backwards, actually. Let's begin from the top right with 2.48%. That's our custom rate package. What made it? A Keras model did. A Keras model that accepted inputs, that information that our sales team has gathered through their dialogue with the prospective seller. That Keras model itself was trained on cloud machine learning engine, and here's where the model stacking happens. One of the inputs to this Keras model is actually a separate model, a word embedding that we've actually used through a few other models as well. One of the other patterns that we're going to talk to today is agility with Yufeng.
Right. So the next kind of thing, the final of our four is agility, right? Lack introduced it with the example of dinosaurs and birds, or eagle in that case. And the implication here being that the world changes, right? That's why you're all here, right? Because machine learning has put down some sweeping changes on the landscape of computing, the landscape of technology. So a couple of kind of models and mental models for thinking about how we can be agile when it comes to data and when it comes to machine learning. The first is failing fast, right? When you have new ideas, finding ways to test out those new ideas quickly and cheaply, right? So if you have a new idea for an architecture for a house, maybe you build it out of Ginger House. Maybe you don't. You use CAD software or something. But I chose to build a gingerbread house, and that's what happened there. So apologies for that. And when you want to fail fast, what you can do is take a subset of your data, right? This new data that comes in. You're like, oh, let me try this out. Let me see if I can get anything useful out of it. But it's not enough to just randomly sample some new data. In a lot of cases, you want to be selective in pulling out a particular subset of that data, the part that is particularly interesting to you. Just because you know that this new data in aggregate is something that is new, something that is different from what you've seen before, doesn't necessarily mean that a random sample will bring about some kind of new insight for you. But if you already know something about the nature of this new data, use it. Use it to your advantage and kind of query your data out and export a chunk of it that is representative of what it is you're trying to evoke. The second aspect of agility is to basically keep developing, right? Just because a model is in production does not mean you're done. In fact, you've just started. You've just gotten across the starting line. I have a model in production now, it's doing stuff. But now we want to continue to improve that model, especially with this new live data. The example of the dinosaur data and the bird data is interesting because once you build your models in production and the new live data is coming in, as soon as that happens, the new data is now your historical data. If you can take that new data and then utilize it to upgrade or update your models going forward. Let's say you deploy your model and 2 months later, you're able to take that 2 months worth of data and do something useful with it. Then you can improve your existing model. You don't need to just use the historical data from the past. You kind of have the recent past. And finally, kind of frequent retraining. This notion of once in a while, you might need to just blow it up and start over. And that's okay. Because whether it's a new model, right, you might train it on a new model, or you might say, this model has been trained on data from the past 5 years, but we started by training the data from like the older 3 of those 5 years. And then the past 2 years that the model has been in production, we've updated and updated and updated. But there's a lot of kind of cruft. It's almost like when you're developing a software system, right? You build that initial release, and then over the next 2 years, you add patches, you put some duct tape here, you add some string over there. And at the end of 2 years, it doesn't even look like the thing you originally designed. And so maybe you start over, you build over here, and you say, let's start and say, if I wanted to build this from scratch today, how would that look like? Would I still use the same models? Would I still even use the same features? As machine learning, a field that's moving so quickly now, as that kind of progresses, it will likely change the answers to those questions, and relatively quickly. And so concretely, what that often amounts to is taking your deployed model and having something like model versioning, right? We all have software versioning, we have Git and things like that, so we should also do the same with models. And one of the key benefits of this is being able to roll back. When you deploy a new version of a model, you want to be able to say, oops, no, I don't want that one. Let me go back to the old one real quick. Or maybe you deploy it and it works. And then the weekend comes. And then you realize your model doesn't generalize to the weekend. So then you roll back. Maybe you have 3 new models and different teams made them and they're competing for saying, hey, it should be mine. And then the other team also says, no, it should be our model. Our model is better. So split testing, being able to divert your traffic in an appropriate manner across different models to say which model is actually the better or more useful model. And so the second point here is, in terms of staying agile, is thinking of your system in this kind of chain, right? From training all the way to deployment, all these different levels of abstraction that you have access to. You might start by working with something like a pre-trained model or something from TF Hub, something that is already well documented, well maintained, and established as a model that works. And as you go along, as time passes, you might become more sophisticated in your approach and customize that model. And maybe you then retrain it and do all these things, but having good layers of abstraction allow you to make these changes without kind of colliding with yourself. And so to talk a little more about agility and how they've approached it at Square, I'll turn it back over to Edmund.
Thank you. So what's this screen here? It's the decline screen. It's what our sellers and their customers see whenever one of our financial partners declines a transaction. We don't like seeing this screen. It represents a lost sale for our sellers, and for us, it's lost revenue from missing out on facilitating that sale. In order to minimize declines, we're actually working on automatically retrying declines. But each decline has a cost, so clearly we don't want to retry everything, because some of those retries will inevitably decline themselves. But we do have a model to help us decide which ones to retry. Now, this diagram's a lot simpler than the other ones I've shown to you. And there's really only 2 key points here. The first is that inference is done in our payment systems, which are written in Java, but training was done in Python using a TensorFlow pre-made classifier. And what that has allowed us to do is to go from nothing to handing off a trained model to the engineering teams to integrate into our payment processing systems. And while they're working on integrating that system, I'm free to continue to collect more data, to refine our model, and to refine our decision criteria. And finally, when it comes time to swap models in and out for testing, it's just one line of code that needs to be changed, not much.
Sure. All right. So to kind of summarize then, parents should develop, operationalize, and maintain ML models. Number 1, need to exactly reproduce the training steps in your deployment system. And as Edmund pointed out, right, the idea is to limit the training serving skew in the machine learning model. So use identical BigQuery queries, use TensorFlow feature columns, use TensorFlow transform. The second pattern is to be portable between different hardware and software used for training and inference. And the point of that is to basically use a system, a machine learning framework that offers you that portability. Don't go for the next new shiny thing. Like there's value in basically going with something that's mature, that's supported on a variety of different platforms. The third aspect of this is basically allowing for flexibility in model development and model deployment. So the idea there is basically to be able to change models, to be able to basically stack models together, to be able to basically do all of these things, to have different versions of a model. All these are very, very, very important in a production system. And when you design a machine learning system, you should plan for your model to go obsolete, for things to be changed, and make sure that your client code doesn't rely on a very specific model, but is basically acting on it through a layer of indirection. And finally, this idea of staying agile, to be able to iterate and to deploy updates. As Edmund pointed out, I mean, their idea was to basically give their engineering team an initial version of a model and then go ahead and keep collecting data to create the next better model. That's a great way to approach it, right? So don't think that you have to build it all at once, but understand that as new data come in, you're going to basically get a newer and better model. But you have to have something out there immediately, right? So don't let the perfect be the enemy of the good. So to summarize then, these are the patterns that we talked about for reproducibility, portability, flexibility, and agility. Number one, joining your data in place, sharing queries, sharing data sets, pre-processing your data using Apache Beam and TF Transform, running TensorFlow on hybrid environments, thinking about training on the cloud, predicting on the edge, gaining flexibility with cloud, with Kubeflow, building the right abstraction level in machine learning, and building in the ability in your systems to be able to roll back model versions and to continuously retrain machine learning models. Thank you.